Welcome to our exploration of the metric tensor, foundational concept in differential geometry and physics. Crucial for understanding the geometry of curved spaces and the fabric of spacetime. The metric tensor is a mathematical construct that defines the geometry of a space, providing a way to measure distances, angles, and other geometric properties within that space. In essence, it encapsulates the shape of the space, dictating how lengths and angles change as one moves from point to point. Unlike the Euclidean geometry familiar from everyday experience, where the metric is constant and distances are measured straightforwardly with the Pythagorean theorem, the metric tensor allows for spaces with varying curvature and complexities. It provides a powerful tool to describe both flat and curved spaces, enabling physicists and mathematicians to understand the geometry of the universe on different scales. The components of the metric tensor depend on the coordinates used to describe the space. These components form a symmetric matrix, representing the inner product of infinitesimal displacement vectors at each point in the space. This inner product defines the scalar product, determining distances and angles between vectors in the space. For instance, in Euclidean space, the metric tensor takes a simple form where the components are constants, like the Kronecker delta, indicating that the space is flat. However, in curved spaces, such as those encountered in general relativity, the metric tensor varies from point to point, representing the curvature of spacetime caused by mass and energy. The metric tensor is pivotal in Einstein's theory of general relativity. In this theory, gravity is not a force acting at a distance, but a consequence of objects moving along paths or geodesics in curved spacetime. The metric tensor describes this curvature, determining how objects move and interact under the influence of gravity. Understanding the metric tensor allows us to compute line elements, which represent infinitesimal distances between nearby points in a given space. The line element is calculated using the metric tensor and provides a fundamental quantity to measure intervals in curved spaces. The significance of the metric tensor extends beyond general relativity. It finds applications in diverse fields like cosmology, where it aids in describing the geometry of the universe on large scales, and in the study of black holes, where the metric tensor characterizes the extreme curvature of spacetime near these cosmic entities. However, manipulating the metric tensor and understanding its implications require a solid grasp of differential geometry and tensor calculus. Its components change with coordinate transformations, and calculating its properties in highly curved spaces demands advanced mathematical techniques. In summary, the metric tensor serves as cornerstone in understanding the geometry of spaces, ranging from flat Euclidean spaces to curved spacetime.